Hey, welcome everybody. Coffee with Caleffi. Thanks for joining us today. This is actually the first presentation of 2021, so welcome to 2021 also, people. Yeah, delighted to have John Sigenthaler as our presenter today, and hopefully you have a comfortable seat and a beverage nearby because we're going to go 90 minutes today, so be aware of that. Of course, it's going to be archived and everything if you have to leave partway through, but a lot to cover. It's a great topic. It's a timely topic, and we've got the right person to present this today. So we got a couple housekeeping slides. We'll roll through these quickly, and then we'll get into it. Thanks, Iggy. Yeah, so this is just a little information if you have trouble with logging in or something like that. Sometimes if you just log out and log back in, it'll fix any kind of connection issues you might have. It could be, the bandwidth issue or something on your connection. So we do send out the certificate of attendance. This goes out electronically, so you'll get this in your email after the presentation. Yeah, an hour and a half today too. So, oh yeah, we're the winners. We're the big winner. Winner, chicken dinner. This is our angle mix valve that took the innovation award at the AHR, which we won't be able to do in person this year, unfortunately. But we've been runner up a couple years, but this year we got the grand prize with our unique angle mix valve there. So we're going to be talking about those in the future a little bit more too. And then yeah, this is a presentation this coming Monday. We're going to do a shop talk showdown. We're going to talk about infrared thermography and how you can use that on your jobs. We're going to have a little bit of a showdown debate between pumps or zone valves with Eric Oni and my son Max are going to do the showdown part of the shop talk. So tune in for that if you can this coming Monday. Okay, what else do we have here? Yeah, and so that's the next month's Coffee with Caleffi. So we're getting that one all tuned up and ready to go on balancing valves. So we'll have the team there that you see on the left from Caleffi doing that presentation. Okay, what else do we have? Oh, there's our boy in person too. You see him above and in the picture. Two Siggies, twice the pleasure, twice the fun.
Well, thanks, Howard. Good to be here. From snowy, wintry upstate New York, we're going to talk about hydronic-based cooling systems. So spring is coming, so is summer. And what we wanted to do with this topic, actually going back to hydronics, and by the way, I want to mention hydronics number 28. That is up as a PDF file right now at the Caleffi website. That'll be coming out in hard copy as well as the digital version in February. And much of what we're going to be talking about today is covered actually in more detail in Hydronics 28. So I want to encourage you to download that. It's fairly lengthy. I think it's 70 some odd pages. When we huddled to decide what we want to do with this issue, we wanted to focus on contemporary hydronic-based cooling systems. So obviously hydronic-based cooling has been around for quite a while, mostly in larger buildings, but there are some new approaches towards hydronic-based cooling, and we wanted to focus on those, and we certainly also wanted to focus on primarily commercial applications. Some hydronics technology in regard to cooling does scale up from residential, but there are things that in the commercial cooling market that really don't scale backwards practically into residential. So this issue of hydronics and what we're going to talk about today primarily focused around commercial. And I won't read all these to you, but we're going to take a look at the beginning. I always like to start off with what are the advantages of hydronics technology in terms of the subject matter. So why should we be looking at hydronic-based cooling? Obviously, there are other air-based and refrigerant-based systems that are out there, and we're going to do a quick comparison of some of those. We're going to look at some of the hardware that's available to provide the chilled water for cooling, and we're going to start off with a basic commercial chilled water cooling system. Typically, it would have a cooling tower, it would have probably a centrifugal chiller in it and a distribution system. And then we're going to look at one way to modify that by adding a heat exchanger, what's called a water side economizer, and take advantage of free cooling when the outdoor temperatures allow it. We're also going to look at very contemporary subjects, radiant panel cooling and also chilled beam. And what's different about these two topics is that fundamentally they separate the sensible cooling load from the latent cooling load. They deal with them independently, whereas a standard commercial chilled water cooling system with air handlers, the air handler takes care of both all the sensible cooling as well as all the latent cooling. We're going to look at water loop heat pump systems. These have actually been around for actually several decades now. They're a great hydronic-based solution when you have a commercial building that tends to have a core cooling load pretty much 12 months a year, certainly in the summer, but even in the middle of the winter, some commercial buildings based on internal heat gain will have a core cooling load at the same time that they have a perimeter heating load. So rather than run a separate cooling system for those core areas and run a heating system for the perimeter areas, we're going to move heat from the core of the building out to the perimeter. And then we'll finish up with what I think is a really cool application, and that is building ice using off-peak electrical energy. So we have inexpensive electricity at night. We're going to run a chiller, and we're going to run it flat out at low temperatures, and we're going to build several tons of ice, and then we're going to use that ice the next day. When the electric rates go up, we're going to turn the chillers off, or certainly turn them down to minimal capacity, and we're going to use the cooling effect stored in that ice to cool the building. So we've got quite a range of topics to talk about here. So let's start out with I guess you'd say the very rudimentary form of cooling. I think obviously we weren't around back then, but any of you that have ever been in a cave or even a recessed cavity like this know that I'm sure early civilizations sought these areas out, especially in warm climates, simply to get out of the sun and perhaps get far enough into that cavity that the temperatures were tolerable. The Egyptians took it a next step. They discovered that by putting reeds, hanging reeds in window openings, or just openings in the exterior walls of their buildings, and then dripping water down along these reeds. They were essentially using the reeds as an evaporative media. And of course, in those arid climates, low humidity air would evaporate that water, and in doing so, cool that air stream down. So you could look at this as a very early form of what we would call evaporative cooling today. And then this is another really interesting approach that goes back centuries. These are wind towers that are used over in the Middle East. And if you get an opportunity, do some research on these. They actually are very well engineered. They are designed to capture wind, or just moving air, on the upwind side and use the kinetic energy in that moving air to drive that air down through the tower, circulate it through some of the occupied spaces down at the bottom, and then come back up through the downwind side of the tower and leave. So this is really a pretty ingenious system for channeling air and at least creating some air movement. Obviously, it can't really cool it the way we do today or dehumidify it, but in that particular climate, this was an early form of cooling. And of course, when electricity came along, that changed things a lot. Fans were introduced. And of course, a fan can help. It can increase evaporative heat loss from the body. It can increase convective heat loss, but what it can't do is dehumidify. So a fan is a partial solution. And then this guy came along, Willis Carrier. Many of you know his term as the father of air conditioning. And some of the early work that Willis Carrier did was in industrial refrigeration, and eventually moved that early refrigeration-based technology over to some commercial cooling applications like stores and movie theaters. And of course, technology has progressed tremendously. So today we have all kinds of modern equipment that can produce chilled water for hydronic-based cooling. And we're going to take a look at some of those different devices. So as with a lot of technology, going from very rudimentary to state-of-the-art today. So what's one of the big advantages of using water-based, hydronic-based cooling systems? Well, it goes back to a physical property of water. We've talked about it on many past coffees with Caleffi. Water can contain, a given volume of water can contain almost 3,500 times as much heat as the same volume of air. So that's a tremendous advantage in terms of the ability of a material to absorb heat, contain that heat, and then if we can move that material, we can move heat with minimal amounts of material. And just to put that in perspective, in terms of chill water cooling, think about a 2-inch copper tube carrying 40 gallons per minute of chilled water. And that water is going to go through a device, let's say it's the coil in an air handler, and it's going to change temperature. In this case, it's going to go up by 15 degrees Fahrenheit. And if you do the math on that, that's 300,000 BTUs per hour. Okay, 40 gallons a minute going through a 15-degree Fahrenheit temperature change. Now there's a comparison here between that 2-inch tube operating under those conditions, and over on the right side here you see a rectangular and a round duct with the dimensions that those ducts would have to have equivalent heat transport capability. And we've done similar diagrams in the context of heating, but these are obviously very large ducts. They take up a lot more space, as you can see over here on the right. And the other thing to think about with this is heat loss, or in the case of cooling, heat gain. Those ducts have roughly 24 times as much surface area as the pipe. So not only do you have a much smaller conduit when you're using hydronic-based cooling, but you also have less heat gain, substantially less heat gain, especially if that pipe or that duct is going through a semi-conditioned or an unconditioned space. So that's a very fundamental difference between moving cooling effect through a building with water compared to air. And another advantage that I'd like to talk about is what I call distribution efficiency. And I want to stress to you that, oftentimes when we talk about cooling as well as heating, we often talk about efficiency metrics. In heating, we talk about AFUE, or coefficient of performance on a heat pump. In cooling, we may be talking about energy efficiency ratio, or seasonal energy efficiency ratio, or in the case of a chiller, the number of kilowatts supplied to operate the chiller per ton of cooling output. And certainly that's part of the picture. But you also want to take into account the energy that it takes to move that cooling effect from wherever it's generated to wherever it's needed in the building. And especially with a cooling system, keep in mind that every watt of power that is used to move cooling effect in a building is a watt of added to the cooling load. So, in a heating mode, we could argue that this power ultimately is just like electric resistance heat. It adds to the heat input to the building. And we could say, well, that is beneficial, but in cooling, that's not the case. So we want to be able to minimize the electrical power that it takes to move cooling effect from where it's generated to where it's needed. And one of the ways we can put numbers on this is to talk about this simple ratio, distribution efficiency. And it's simply the ratio of the rate of heating, or in this case, cooling delivery in BTUs per hour, divided by the electrical power that it takes to operate that delivery system. So it's the beneficial effect divided by the necessary input effect. So what I did is I just took a look at a residential or light commercial scale geothermal heat pump. It's a water to air heat pump. So it's tied into an earth loop or some type of a water source, but on its delivery side, it uses ducted air. And the data here, the 3/4 horsepower electronically commutated motor that operates that blower up to 1500 CFM, Looking at the specs on that, that requires 690 watts of electrical input just to operate the blower. And the rated cooling capacity was about 53,000 BTUs per hour. So if we put those numbers into that formula, we're just dividing the cooling effect, 53,000 BTUs per hour, by that power input to operate that blower. And we're getting this number here, 76.8 BTUs per hour per watt. And the way to interpret that is just put a 1 here in front of the word watt. So for each watt that we are supplying that particular system to distribute that cooling effect, it is delivering almost 77 BTUs per hour where it's needed. And of course, by itself, that number doesn't mean much. So let's do a comparison. Let's compare it to a hydronic circuit. And I try to pick something that would be equivalent in terms of capacity here. Let's assume it's a 200-foot equivalent length. So we've got some pipe, fittings, valves, and so forth in there. But we've done our math, and we found that's equivalent to 200 feet of 1-inch copper tubing. And we're only going to operate that with a 10-degree Fahrenheit temperature change. So if we're supplying chilled water at, let's say, 45 degrees Fahrenheit, it's going to come through the coil or whatever that delivery system is. It's going to come back 10 degrees warmer. Oh, I'm sorry, we have it across the radiant ceiling panel here. The hydronic system uses a circulator. Again, it's an electronically commutated motor, a modern motor in that circulator. And we're going to assume that that particular circulator has a wire to water efficiency of 40%. And what that means is that 40% of the electrical energy supplied is actually being converted to mechanical energy, which we call head in hydronics context. And that's what's creating the movement of the fluid through the system. So if we put a simple calculation together where we divide BTUs per hour by 500 and delta T, 10.6 gallons per minute is what we need to deliver, and that's within the capability of that 1-inch copper tube. And here's another formula we can use to estimate power input to the circulator. And it's essentially a constant that makes the units work out correctly, times the gallons per minute flow rate, times the delta P. This would be the pressure difference, the pressure drop in that circuit, 5.6 PSI. And this is that wire to water efficiency of 40%. So this formula estimates roughly 65 watts of power input. Now, I'm going to add to that a blower, because realistically, we're going to have to do some latent cooling. We're going to have some kind of a coil to remove moisture. We don't want to do that just by condensing on a radiant ceiling. So I've added another 150 watts to account for the power input to that blower to do our latent cooling. So our distribution efficiency, including the power of both the circulator and the blower, works out to be 247 BTUs per hour per watt. So when we compare it over to the left side here, this particular snapshot of this system, we're delivering cooling using about 36% of the electrical power that the forced air system required. And I do want to point out that of that, only about 9.6% was actually required by the circulator. Right here, you can still see that even though it's a small fan, it still adds significant wattage, but we need the fan there in that coil to do that latent cooling. Okay, so hydronic systems, again, leveraging the heat capacity of water over the heat capacity of air and reducing the amount of power that it takes to move cooling effect through the building. And of course, today we've got a lot of choices on the hardware that we use to produce the chilled water. In a larger commercial system, it could be something like this. This is a centrifugal chiller, okay? Or it could be an air-cooled chiller that sits up on a roof. We've got multiple compressors, multiple fans, multiple staging capability on a device like that. Up here, we're looking at, this is actually a commercial building that has 2 5-ton rated water-to-water heat pumps, geothermal heat pumps. So you can see they've built a rack They've set it up so the heat pump is serviceable and all the piping that needs to be insulated there is insulated. Over on the right, we've got a relatively new device. We're going to talk about it a little bit more. It's called a heat recovery chiller. So this is a device that, rather than taking all the heat of rejection that we produce during cooling operation and just blowing that off to the outside air, this device has another flat plate heat exchanger in it, and that can take some of that hot refrigerant. Instead of just running it through the air-cooled condenser, we can run it through a water-cooled condenser, and we can produce a stream of warm water simultaneously with a stream of chilled water. And we can do various things with that warm water. We might use it to heat a pool. We might have a process load. We might be using it to preheat domestic water. Okay, so that's an interesting device. Lower left corner here, this is a photo that shows 6. These are nominal 5-ton air-to-water heat pumps. They're set up on a commercial building. These actually supply some chilled beams that we'll be talking about later on. But it's a staged air-cooled condensing unit, but it can also provide warm water for heating. You jump around a little more exotic technology right here, the large plate and frame heat exchangers. This is part of a lake water cooling system up in Toronto, Ontario. I forgot what the exact tonnage on that is. It's a massive system, has pipes that go something like 3 miles out into Lake Ontario from downtown Toronto. And these heat exchangers are essentially the interface between the lake water and the water that goes through the district cooling system. It serves several of the large high-rise buildings in downtown Toronto. Over here, we've got kind of a unique device. This is a lake water heat exchanger. It's essentially a set of welded stainless steel plates that are assembled on a frame. And these plates are set up so that there are hollow channels between the plates. And you can see the large piping here. This is high density polyethylene. That's being lowered into this lake or this large pond. And that's going to become the heat exchanger that will supply a geothermal heat pump system. And it is conceivable in some situations, especially northern locations, that the water at the bottom of a lake in Wisconsin or upstate New York really doesn't get very warm, even the hottest day in the summer. It's going to stay there right around its maximum density point, around 39, 40 degrees Fahrenheit. So it's possible with enough surface area that you could do direct cooling. And the nice thing about this is you're not pumping lake water through your equipment. So you don't really have to worry about debris or fish or whatever coming into your heat exchangers. This is a closed circuit system. And then finally, over on the right, you can also set up some direct expansion condenser units, just like standard air conditioning condenser units. And these can go in and they can supply refrigerant to water heat exchangers. These will be brazed plates typically, and I'll show you a slide of that later on. And you could do dedicated cooling that way. So again, one of the advantages of hydronics, you've got a lot of different source equipment to work with, okay? I put down exterior aesthetics. You know, how do you describe the aesthetics of what I affectionately call window shakers? And you know, here's a location where you've got exterior windows and you've got the window air conditioners, and they work. We've used them. Many of us have used them. They aren't very efficient. They don't do a very good job of distributing chilled air or cool air throughout a space, or especially a building with multiple rooms in it. You take them out in the winter, put them back in the summer. They are what they are. They're kind of the low end of the totem pole in terms of potential commercial cooling. And then we move to something that I think probably everybody here has experienced at times. If you've ever stayed in a hotel, a package terminal air conditioning system, a PTAC. Cut a hole in the exterior wall, put this unit in, and you can turn it on in heating, you can turn it on in cooling. It's a heat pump. I'm not very fond of the comfort that these things create. I usually will take the chair that's at the desk in the hotel room and shove it up against this thing just so it doesn't blow things around and just create these really high air velocities. But it is an accepted commercial cooling option. We can move on to something a little more recent, ductless mini splits, where we've got an outdoor condenser unit. We've got some kind of a refrigerant line set that goes in. Here's a photo of one that actually serves 4 different interior cassette units. And you can see you bring all these line sets outside, as well as all the electrical connections to operate these interior units, bring everything together outside. So it works. It is capable of operating in zoning. So you can turn on any one of those 4 units independently of the others. What you can't do with this system is you can't operate one in heating and another one in cooling at the same time. So the first one that gets turned on sets the mode of operation, and then you can operate the other units as you need to. But obviously that compromises the aesthetics a bit. Rooftops, very common in commercial construction. All air systems, put a curb in, seal it down to the roof membrane, and put this unit on top of it. And then I had to throw a couple more, and these are both fairly close to where I live, upstate New York. This is actually a town office building. I'm not sure who made the decision on how they're going to heat and cool that building, but they have a pad-mounted unit similar to a rooftop unit, but different types of duct connections to it. And they have all this exterior insulated duct. So beyond the aesthetics of this, again, this is a cold winter climate situation. These units are, if they are operating in the heating mode, certainly there's going to be heat loss to the outside, plus the deterioration of the insulation material over time. This is one of the dollar type stores. Again, upstate New York. We've got ducting with insulation on it. One of the other things I look at here is this metal roof. This is in a location where they easily get 100+ inches of snow in a winter, and sometimes that's going to slide off of that roof. And when it does, it's probably going to land right about on top of those units or on top of that ducting. So from an aesthetic standpoint, these don't excite me too much. Okay, oops, hang on. We just jumped out of our software there. Here we go. Here we go. Okay, earlier I was talking about a heat recovery chiller. And the basic idea with heat recovery chiller is you have 2 condensing heat exchangers in there. You have one that can condense and drive heat rejection to outside air. You have another one that can take that heat and put it into a stream of water. And the refrigerant flow is managed between these 2 condensers. If there's no need for a stream of warm water, all the heat would be rejected to the air-cooled condenser coil. And if there is a large demand for warm water, there would be less and less, and perhaps none of the heat of rejection would go to the outside. It would all go into the warm water stream. So it is a way to recover what would otherwise be wasted heat. Okay. And in Hydronics 28, there's a couple diagrams on how these can be set up. It's essentially a 4-pipe distribution system. So we've got a chilled water supply and return pipe. We've got a warm water supply and return pipe. This particular configuration shows a 6-port motorized valve. If you've never seen one of those, you can think of 2 3-way valves with a common actuator on it. And essentially what that valve does is it connects an air handler to either the chilled water piping system or to the warm water piping system. It's basically a toggle, one way or the other, depending on what that particular air handler needs to do at the time. So when we have multiple air handlers in a system, we do have the option with this equipment to operate any air handler in either heating mode or cooling mode, provided we have ample capacity down here. Now, another approach would be to use just 2 zone valves. It's still a 4-pipe distribution system, but the zone valves determine which coil, and you can see these are 4-pipe air handlers. So there are 2 coils in these air handlers, as opposed to a single coil up here. So a little more elaborate design in the air handler, but simpler valving down here. Both of these systems can make use of variable speed pressure regulated circulators. Both of them should be equipped with air, dirt, and magnetic particle separation, especially with the permanent magnets in these high efficiency circulators. And again, there are more details on this type of system in Hydronics 28. Earlier, I showed you a photo of a couple outdoor condensers. Here is how we would tie those refrigerant line sets from those 2 condensers back to a couple brace plate heat exchangers. We do have staging capability here. When you do this, it is very important that you put flow switches in. If a circulator fails to turn on for whatever reason and the condenser unit turns on, remember the condenser is trying to chill the water inside that brace plate heat exchanger, and there's not much water in a small brace plate heat exchanger. It might only have a quart of water in it. So in very short order, that could freeze that water solid, possibly split the heat exchanger. So the controls in a system like this would use a flow switch. The control sequence would be the circulator would be turned on. The flow switch would verify that there's adequate flow, and assuming that verification takes place, then the condenser unit that's associated with that particular heat exchanger would be turned on. So again, a failure of a circulator with a flow switch is going to detect that and prevent a freeze up on the brace plate heat exchanger. I also want to point out this diagram assumes this is strictly for chilled water cooling. So in a normal system that we would use a buffer tank, let's say for heating, we would be taking water off the upper portion of the tank and going out to the system with that. But if it's a cooling only system, we want to take the water off the lower portion of the tank. That's where the coolest water is. Remember, as you cool water, you increase its density, and the higher density water will tend to collect near the bottom of the tank. So again, we could use a variable speed circulator. We could go up here and use zone valves and go to multiple air handlers. Okay. Here's a photo. This is actually from the same installation as these condensers. There's a couple Caleffi flow switches installed. You can see the insulated piping. You'll see that the body of the flow switches is insulated, but not the portion of it that actually has the electrical components in there. We don't want to get that to the point where it potentially could get cold enough to have condensation in it. Okay. All right. Now let's move to what I call a traditional chilled water cooling system. And I've kept this very rudimentary. We'll start with the chiller. It could be a centrifugal chiller. It could have reciprocating or rotary screw type compressors, but fundamentally it has an evaporator where we are chilling the water down by evaporating a refrigerant. That water is then circulated up to a coil in an air handler, and the air that gets blown past that coil is typically a combination of outside air that comes in through a damper and return air. So we have some type of mixing damper assembly here that, depending on the time of day, depending on what the load is, depending on what the ventilation requirements are, we can mix a certain portion of outside air with return air and deliver that through the coil for cooling, dehumidification, and then eventually out through the ducting system. The other side of the chiller is the condenser. This is where the heat of rejection goes into a stream of water, and I'm showing it pumped through a closed circuit cooling tower where we've got some type of media with tubing strung through it. We have a sump with water at the bottom. Now this water is not the same as the water in the closed circuit. This is just fresh water. We have some kind of a makeup water system on there. Usually a float switch would determine what the water level is in the sump of the cooling tower. We have a circulator that's going to turn on, and basically it's going to pump water up through a series of nozzles that's going to spray water down over that media. And you're going to get a combination of cooling effect simply by the air coming through here, as well as the evaporation of water. And keep in mind, every pound of water you evaporate is approximately 970 BTU. So evaporating water is a very effective way to remove heat. So that's a standard, very basic chilled water cooling system. There's an example of a commercial cooling tower. Again, that centrifugal chiller, really nice insulation job on that chiller. And then the coil in the air handler, I'm showing a very deep coil, and what that implies is several rows of tubes. So we get a very good latent cooling effect there, very good moisture removal from the airstream. Okay. Again, air handlers. These are, I would say, probably the default terminal unit in most hydronic cooling systems. In smaller applications or in applications where we have several zones, independently controlled zones in a building, we can install multiple air handlers. Here's an example of a horizontal air handler. Again, it fundamentally is a combination of a coil, a heat exchanger between the water and the air, and a blower that goes provides the forced airstream out through ducting. Vertical air handlers are also available today. Actually, several companies offer air handlers that can be configured for either vertical or horizontal installation. Essentially, you open up one end of the unit and you change the orientation of the coil. Most of them use what's referred to as an A coil. And you see there's multiple connections down there. Basically, when you change it from vertical to horizontal, you use different connections for different drain pans. Here's an example of a small horizontal air handler that's mounted in a space. It's a conditioned attic space in a commercial building, and it's above a finished ceiling. So obviously, we do not want any water that could, over time, potentially leak, condensate water that could leak out of that air handler. We don't want that down on the drywall ceiling. So it does use a secondary drain pan. It's a little hard to see it. It's right here. The other thing it has is a switch that can detect if condensate is backing up in the drain pan. For example, if the piping that takes that, normally would take that condensate either outside or to a drain system, if something gets plugged up and that pan starts to fill up with water, that switch is going to disable chilled water flow as well as blower operation in that air handler. And that's simply to prevent an overflow of water that could damage the ceiling down below. Here's another installation. This is a 3-ton horizontal air handler. You see the two, this is 3/4 inch pre-insulated PEX tubing that supplies chilled water to it. Return air on one side, supply air on the other. It's in a conditioned cavity. The space above this oriented strand board here is insulated. So this is not going to freeze up in the wintertime. And there's eventually either going to be doors or a bookcase that would slide in. The point I want to make is you don't want to build this where you can't access it. You always want to make sure you have access to service, and if ever necessary, replace that air handler. Going from small to medium here, this is a large commercial application. You can tell from the piping over here, there are 2 independent chilled water coils here. The small piping, that's the condensate drain with a trap, okay? And that's in a some type of a cooled warehouse assembly. It's not ducted. You can see the air filters on the back here. So basically, it's just a free air circulation in that facility. And then finally, this is a very large custom-built commercial air handler in a sports arena. You can see it actually has a door on it. You can get in it, just to give you some idea of the scale of this. These pipes out here, they're covered with a jacketed insulation. They supply heating coils, cooling coils. Something this large probably has a heat recovery system built into it. It could have several stages of air filtration built into it. It could have humidifiers. It could have ultraviolet light to kill bacteria, viruses. Typically, when you get up into something at this scale, it's custom built for the application. Now, going back to smaller scale, chill water fan coils. Bottom line is you should only use fan coils that have drip pans for chilled water cooling. Remember, you're going to be condensing moisture from the air, and that condensate's got to go somewhere. And without a drip pan, it's simply going to come down and run out on the floor and do damage. So some different products here. This is a contemporary looking fan coil unit. It's got a nice coil in it, tangential blower down here with a electronically commutated motor. Meissen makes that. It's called an I-Vector. These two products up here from Yaga, North America. I want to just show them as examples of recessed air handlers, or I'm sorry, fan coils. These do have drip pans in them. You can see the drain here. High wall units. A high wall unit looks more or less identical to a ductless mini split cassette unit. Really, the only difference is it has a water coil in it versus a refrigerant coil. It's turned on and off by a remote. It's got a damper that opens when it operates down here at the bottom. It's got internal filters. Air goes in at the top and discharges out through the front here. And then again, some contemporary looking console fan coils. Here's one that's actually been built right into the wall. So there are various products that are out there that can do both heating and cooling. But again, the takeaway, if you're going to use these for chilled water cooling, make sure they're equipped with drip pans. Okay. Now, distribution systems, 2-pipe and 4-pipe. A 2-pipe distribution system up here. I'm showing it as if it just has a chiller connected to it. Remember, chillers need to have certain minimum flow rates when they operate. So that flow rate may not be the same as the flow rate if we only have one air handler on. And again, consider this a system that has a lot more than 2 air handlers in it. I'm just kind of truncating it here. So let's say we're under a partial load. We need a certain minimum flow rate in that chiller. We could put in a hydraulic separator, and that separator is going to do multiple things. It's going to decouple these 2 circulators. So the flow rate in the chiller can be whatever it needs to be. The flow rate in the distribution system can be, again, what it needs to be based on what zone valves are open. And they don't have to be the same flow rate. So we're decoupling the flow rates. We're decoupling the pressure dynamics of these 2 circulators. We're also doing air separation. We've got a coalescing media in there. And we're doing both what I'd call standard dirt as well as magnetic particle separation. And again, anytime the system involves the newer high efficiency circulators with the permanent magnet rotors, I would certainly recommend some type of magnetic particle separation in the system. You don't want that magnetite ending up inside that circulator. So the takeaway on a 2-pipe system, these air handlers can turn on and off independently of each other. And the distinction here is you cannot have one air handler operating in heating mode at the same time another one is operating in cooling mode. And with this system, it's pretty obvious because there's only a chiller. But it is conceivable that we could also put a boiler over on the left side of the separator with its own circulator. And in the winter, we could operate a 2-pipe distribution system on heating. Now again, these individual air handlers can turn on and off independently, but the entire system has to operate in either heating mode at a given time or cooling mode. So that's the limitation, if you will, of a 2-pipe system. You can overcome that with a 4-pipe system, albeit with more complication. We've got each air handler equipped with 2 coils, a heating coil and a chill water coil. We've got 4 pipes here. We've got a chilled water supply and return as well as a heated water supply and return. Our zone valves simply open depending on are we operating that particular unit in heating or in cooling. And then over here, again, I've shown what could be a variety of different hardware. We could have a chill water source. It could be a buffer tank that's supplied by, for example, air to water heat pumps or geothermal heat pumps. And same thing down here. We could have a heated water buffer tank. So really the main takeaway is, do we have a building where we want to provide the ability to do simultaneous heating in some areas, cooling in other areas? If that is the case, the 4-pipe system tends to be the default design approach. Okay. Now we're going to take the basic commercial chill water system and add some more detailing to it. What we're going to do is we're going to add a plate and frame heat exchanger down here. And we're going to use that heat exchanger as a, if you will, a partial or a full replacement for the chiller when we can keep the heat exchanger at a low temperature based on outdoor conditions. So right now, the system you're looking at over here on the right, this is in what I call 100% chiller mode. Okay, so we've got our chiller, the condenser water, the warm water from the condenser is going out through our cooling tower, coming back. We've got a diverter valve here that's diverting it back up. So we've got basically a closed circuit on a condenser, taking heat, dumping it outside. On the evaporator side, we've got water coming, well, let's start at the distribution. We've got warm water coming back from our air handlers. It's again hitting a 3-way motorized diverter valve, and it's going through the upper part of the hydraulic separator. Again, we're sending the warm water through the top of the separator because it's going to have the lower solubility for dissolved gases. That's where we want to capture those micro bubbles and get them out through that air vent. We're going to send the warm water through the evaporator. We're going to cool it down, send it back through the bottom portion of the hydraulic separator, and then back out to the system. So in this particular mode, our plate and frame heat exchanger, what we call the water side economizer, isn't doing anything. This might be the mode that we're operating in when we have a very hot, very humid outdoor condition, okay? Now, let me go on to another mode here. This is 100% economizer cooling. What we're doing now is we're shutting off the chiller, and let's assume the outside temperature is maybe 40 degrees, okay? So we're taking our warm water that's coming back from our air handlers. The diverter valve has switched position now, and it's sending it over. We're going through our air and dirt separation, and we're going into one side of our plate frame heat exchanger. The other side of that plate frame heat exchanger is connected to the cooling tower circuit. So if it is 40 degrees outside and we're circulating water and blowing air and spraying a water mist over this coil, we're certainly getting a good cooling effect. So we're creating chilled water in our cooling tower, and it's simply coming back and going into the other side of that plate frame heat exchanger. So you can think of the heat exchanger in effect as replacing the chiller as far as providing the source of the chilled water, and then we're simply taking that and running it back through the distribution system. So I've shown you both extremes of this system, 100% chiller operation and 100% economizer. We can also have an economizer pre-cooling function. And what we're doing here is we have conditions outside that do enable us to do some cooling on our warm water coming back from the air handlers, but we're not getting that temperature low enough to go directly back out to the air handler. So we're pre-cooling the water using the heat exchanger, but then we're also sending it back up through the separator, circulator. We're going through the evaporator. Keep in mind now that our chiller is a variable speed, so it can slow down and adjust its cooling capacity based on what the water temperature is coming in. We're getting our set point on chilled water coming out of the evaporator, back through the lower portion of the separator and back out to distribution. So we're getting a partial free cooling effect, or I use the term free cooling. It's not really free because we're running fans in the air handler, in the cooling tower, as well as circulators, but our power input for this mode of operation is definitely lower than if we're supplying all our cooling effect through operating the refrigeration cycle in the chiller. And there are some ASHRAE standards now that require at least an evaluation of water side economizers in certain climate zones. I don't have that information on the slide, but it is in Hydronics number 28. Okay, and just to show you this concept in another form, some manufacturers now offer air-cooled chillers that actually can be ordered with a section of heat exchanger. This is basically all hydronics back here, okay? And conceptually what's happening here is we're sending our warm water up, and we have a control system that decides based on the outside temperature and also based on that temperature of that entering water, do I need to run the refrigeration side of the system? Do I need to run it at partial capacity? Can I keep it completely off? If I could keep it completely off, I'm simply going to direct the warm water over to the water side economizer module. So essentially we're sending that water through coils and we're running the fans to chill it down. If we need partial operation on the refrigeration system, our modulating valves can determine what flow proportions go each way here. And with these modular fans, we can control what fans are on. So these are pretty interesting devices in the sense that they have a lot of capacity control. They can take advantage of low outdoor temperatures for this economizer mode of operation. And they can certainly that can all be coordinated with a building operation system, building management system. Okay, now we did want to do some poll questions just to, again, get some feedback from the audience. And our first poll question is, how often do you incorporate water side economizers in your commercial cooling system designs? And Mary, I'm going to let you run that poll and we'll get some results here momentarily. Again, just looking at what's the take up on this. Okay, so the poll is in progress, and then Bob, I'm going to let you give a quick summary of what our polls are here. Okay, looks like the poll, there it goes. Bob, do you want to talk through that one?
I can take it over here, John. It's Cody. It looks like our winner there is seldomly with 44%. We do have significant usage in the 15% range, and often is about 10%, but never is still sitting at 32. So there's use out there. Okay.
So again, this is a newer, a contemporary approach. I do think you're going to see this approach emphasized more. Certainly it does reduce electrical energy use, and it's especially appropriate. One of the things I should mention, it's very appropriate when we have a high sensible cooling ratio. For example, cooling a server room where we don't have a lot of moisture removal necessary. Because what that does, because we have high sensible, we can actually bring the economizer on and keep it on to warmer outdoor temperatures and still satisfy the cooling load. If you have a very high latent cooling load, a lot of moisture removal, obviously once you start to you get that water coming back from the cooling tower, once it gets to the point where it can't really adequately remove moisture at the coil, obviously you've got to bring the chiller back on to do it. So you have high sensible cooling ratios, and again, Hydronics 28 talks about that quite a bit, how to gauge what the sensible cooling ratio is for a given application using psychometric charts. This is a good application for that. Okay. Chill water piping insulation. Okay. Certainly those that are watching the webinar, if you've done chill water cooling, you can all relate to this. And if you've never done chill water cooling, you're thinking about it, I cannot overemphasize how important this is. You can make a mess in a hurry with chilled water piping that's uninsulated. Remember, that piping, the surface of that pipe is going to be well below the dew point of most interior air, especially in the summer, especially if you're starting a cooling system with relatively high indoor humidity. And your piping and every piping component, every pump, everything in that chilled water that's in contact with that chilled water is going to have condensate form on it in minutes, and a few minutes more, it's going to be dripping all over the place. So now I threw this out at the guys at Caleffi just to see if they knew what it was, and the good news is they did. They remember back to their college lab classes, and some of you are probably looking at that and thinking, yeah, I know what that is. I used one of those back 40 years ago. If you've never seen one of these before, this is called a sling psychrometer. And you'll see there's two thermometers on it. Excuse me. One thermometer just has a normal bulb on it. The other thermometer, same type of thermometer, but it has this cotton wick over the bulb. And what you do with this is you saturate the cotton wick with water, you pick it up by the handle here, and you literally spin it around in the air for about 30 seconds. And what that does is it causes a rapid evaporation of water from that wick, and that wick will eventually cause that one thermometer to stabilize at a temperature that is lower than the temperature on the other thermometer. So we would say the thermometer without the wick, that's measuring the dry bulb temperature in the room. The thermometer with the wick is measuring the wet bulb temperature. And there is a relationship between dry bulb temperature, wet bulb temperature, and humidity. And there's a lot of different ways to look at it. You can look at it on a psychometric chart. Okay, you can look at it as this graph here. But basically, if we know, for example, if we know that the dry bulb temperature in the space is 75 degrees, and we know that the relative humidity is 30%, we can use this graph to look up the dew point, and the dew point would be the temperature at which condensation starts to form. Anything at or below the dew point temperature is going to have condensation on it. You can do the same thing here with psychometric chart, dry bulb temperature. These curves represent relative humidities, and then the lines that go at an angle represent the wet bulb temperature. So there's multiple ways. Of course, today you can hop online and find software that'll let you put in any two of these three parameters, and it'll calculate what the other one is. But I wanted to include some photos here that shows what happens when you have components in a hydronic system with chilled water and those components are not insulated. And it doesn't really matter whose product these are. In the upper right here, you can see here's a hydraulic separator. It's covered with condensation. So is the CPVC pipe, the copper, the brass, everything that has chilled water going through it is covered with condensation. Here's a commercial circulator. Excuse me. You can see I'm sure there's been condensation on this pump volute, but you can see up here where there isn't as much paint or on these steel pipes. Surface oxidation happens very quickly. Here's a small residential circulator with a cast iron volute. Again, this is not a raw cast iron volute. It does have whatever the manufacturer's coating is, but within a few weeks of operation, that's what the outside of that volute looks like. And you can see even on the flanges, the zinc coated flange bolts are starting to oxidize. You'll find the handles on the isolation flanges will start to oxidize. So it's really important if you're dealing with chilled water that you insulate components. And there's a table, and again, I took this right out of Hydronics 28. Excuse me. What this table is, this is for elastomeric foam insulation, and it shows recommended thicknesses based on what the surrounding atmospheric conditions are. 85-degree dry bulb, 70% relative humidity. If we're dealing with a pipe between 1.25 inches and 2 inches, and our fluid temperature is approximately 50 degrees, 3/8 of an inch thickness of an elastomeric foam is adequate to prevent surface condensation. If we go to lower chill water temperatures or chilled fluid temperatures, you can see the insulation thickness increases. Now, with this type of insulation, it is very important. Not only do you put it on the pipe, but you glue the ends together. You make sure the seams are going to stay together. When you do insulate motors or zone valves, you don't want to cover the zone valve actuator or the motor of a circulator with insulation. There's some heat generated there, especially in a circulator. If that circulator is operating in heating mode and you insulate the can of the circulator, you're going to overheat the circulator. So here's a couple zone 1 valves that have the body insulated with an elastomeric foam, and the actuators are not insulated. And I did want to show you these. We've used these on projects. I really like these. They're a polymer material. They're designed to go into a channel strut. Here's a picture of it. It's made by Holright. And what this does is it mechanically supports the pipe on these ribs, but it also allows you to push insulation in from each direction so that the insulation is almost continuous across the support. It of course isn't right at the middle, but a bead of caulk, a bead of silicone caulk right around this perimeter would seal that up so that we aren't going to get condensation after several hours of chilled water circulation. We don't want condensation dripping out of that. So that's a product that you can get. And then finally, here's a photo. This just shows some insulated piping on some base mounted circulators. They've used an elastomeric foam. And I'll admit, it's quite a challenge when you have these various shapes to these components to get that insulation and get it continuous. But you do need to do that to make sure you don't have condensation. Okay. Just some photos of nice looking commercial insulation. This can be a fiberglass insulation, but that PVC jacket is effectively becoming the moisture barrier. Down here, this is actually an exterior buffer tank and a combined air and dirt separator. All that piping has been insulated and it's got PVC jacketing on it. And just some other insulation materials. Again, a foil wrapped fiberglass. The foil would act as the vapor barrier. Foam glass, a cellular glass product. Really interesting stuff, totally inert to mold and so forth, but fairly expensive. We can get elastomeric foam that does have a jacket on it. That jacket is primarily for ultraviolet light protection if it's used outside. And I'm just showing you, here's a piece of elastomeric foam, and you can see some of the cement. This is a contact cement that you would put on when you're going to join this together. So again, pay attention to the seams, the butt joints. If you're going around an elbow, I like to 45 miter it, glue it together. It looks nice when it's done. It is a painstaking process if you want it to look good when it's done. And again, make sure everything is fastened together so you don't get condensation. Now we're going to move from traditional chill water systems where we're using a coil in an air handler to do cooling. We're going to move to systems that separate latent and cooling, sensible and latent cooling loads. And radiant radiant panels in general are one example. Here's an example of a typical commercial application where we've got a structural slab. We're going to put some insulation, probably a foam board insulation, a polystyrene material. And we're going to fasten tubing down to probably a layer of welded wire fabric. I'm showing 6 to 9 inch tube spacing. The tube spacing for cooling tends to be closer than what you can use for heating. And then that's going to get a topping slab, typically about 1 inch over the top of the tubing, and then probably some type of a hard surface flooring. I do have a graph down here that gives you approximate outputs. What this is the difference between what is called the operative temperature of the room and the average water temperature in that panel circuit. Operative temperature is the average between the dry bulb temperature of the air and the mean radiant temperature of the surfaces in the room, excluding the surface that you're cooling. Again, Hydronics 28 goes into more detail on that. But fundamentally, as we get a greater temperature difference between the water in the tubing and the operative temperature of the room, you can see our cooling fluxes go up. And those fluxes are determined based on tube spacing. So I'm showing both 6-inch and 9-inch tube spacing. And then whatever the resistance of the finished floor is, from a bare slab with R0 up to a slab with R1 insulation or R1 floor coverings on it. And the cooling flux is BTUs per hour per square foot. Here's a photo. This is a product, I don't believe it's currently available from Uponor in North America, but in other global markets. It's basically a grooved styrofoam panel. You can see the installers putting these aluminum plates into the grooves. There's PEX tubing that's going to go into the grooves. And then there will be some type of a wall finish over this. This is going to be a radiant panel, and it could be very effective in both heating and cooling. Critical detail, we do not want to get any of these radiant panels or the chilled water piping leading to them. We cannot allow those to get below dew point. Nominally stay about 3 degrees above dew point so that we don't cause surface condensation or condensation up there above a radiant ceiling, for example, on piping or piping components. This is actually another way to do radiant ceilings. It's using preformed aluminum plates. This is 1/2-inch PEX aluminum PEX tubing. I've got some formulas over on the side here that would let you get an idea of what the cooling flux would be as a function of the water temperature, or I should say the temperature difference between the water in the tubing and the room temperature. This is going to have 1/2-inch drywall fastened up to it. So again, radiant panels that have been around for decades. Certainly we've talked about them quite a bit for heating, but they are ideal for sensible cooling. They can do the majority of the sensible cooling. They cannot do moisture removal. I shouldn't say they can't do moisture removal. They can, but you don't want to go there. Now, another approach with radiant ceilings is a modular approach. These are products from Zehnder. These are steel panels that have copper tubing, and Zehnder has different products available. Some of these use a graphite layer to distribute heat or cooling effect between the tubing and the surface of the panel. Others use aluminum plates to do that. And then there's an insulation material on the back. And these are designed to drop into a suspended ceiling grid. The connections are typically made with just push-on fittings and small diameter corrugated stainless steel. Remember, these are not insulated connections because, again, we do not allow these panels or the piping that supplies them to get down to dew point. These panels can be installed a couple ways. This is an interesting approach. This is called a cloud installation. You can see the panels are actually suspended. So there's airspace up above, and you'll actually get a higher cooling output per square foot because you have more of the panel exposed to the room. Here is a view up above, and you can see the small diameter corrugated stainless steel connections here. The panels themselves, they do have some weight. They aren't extremely heavy, but they do have enough weight that they do need to be supported on light gauge cables or light gauge chains up to a structural ceiling. And the other way these can be installed is with a flush mount. So the bottom of the panel is flush with the bottom of the ceiling tiles. Cooling output's a little bit lower because of the top side not being exposed directly to that living space. Just to give you some idea how these perform, 58-degree entering water temperature in a room with a 75-degree dry bulb. We're getting cooling fluxes in the range of 30 to 35 BTUs per square foot. That's with the flush mount. If it's a cloud mount, you can see pretty significant increase in output at the same water temperature because of more surface area exposure. Okay, so We've talked about radiant panels as cooling terminal units. Leads us up to another poll question. How often do you use modular radiant ceiling panels like we just took a look at for cooling? So go ahead and enter that in, and I'm going to pause for a moment right here while those answers are coming in.
Big numbers on this one. So again, some of these are available in the US now. I think Zender's got some manufacturing somewhere in New York, don't they, for some of those?
Yeah, they do. They're out near Buffalo.
Yeah, out in my hometown.
They're all stomping grounds there.
Looks like it's moving a little bit, so. Yeah, there you go, 76% never. Seldom 21%, significantly 2%, often 1%.
Okay.
Yeah, never by large margin.
Yeah. Well, again, we're introducing this concept in, well, I shouldn't say we're introducing it. We're talking about it in hydronics because, again, the overall trends towards building electrification, cooling, increased number of buildings that need cooling. When you're looking at this from the standpoint of reducing energy use, there are significant advantages. And again, in Hydronics 28, we go into this in more detail, but to summarize, if you can move a significant portion of the sensible cooling load, and average conditions, for example, in upstate New York, we would say about 70% of the total cooling load is sensible cooling. The other 30%, latent cooling, moisture removal. So sensible cooling is the dominant portion of the cooling load. If you can move the majority of the sensible cooling load to water side distribution versus air side distribution, we leverage what we started with on the webinar. We leverage much lower pumping costs compared to the cost to operate large blowers to push that air through the building. And that is that's primarily the driver behind both radiant panels and what we're going to talk about next year, and that will be chilled beams. Now, a chilled beam is a coil. So we have aluminum fins, we have copper tubing. You can see it in cross section right here. And that coil is in an enclosure that is designed to either be suspended from a ceiling or to drop into a suspended ceiling grid. And we're going to supply that unit with chilled water, but again, water above the room dew point. Chilled beams are not designed to dehumidify the air. So we have to have controls that make sure that we do not allow that chilled water to get down to dew point temperature. And the other thing that we're going to supply, most of these chilled beams are specifically what are called active chilled beams. What that means is that we're going to introduce ventilation air, very dry ventilation air, where that incoming air has been preconditioned at an air handler so that it is very dry. And what's going to happen is that dry air, just think of it as a dry sponge, and you're going to introduce that dry sponge into a space that has humidity. It's going to soak up that moisture in that air and maintain the humidity level in that room to acceptable comfort conditions. Now, the dry air is introduced into the unit and it comes out through orifices, and that introduces an airflow that induces warm air to flow upward through that coil, get entrained by the ventilation air and mixed with it, and then discharged out through there. The ventilation airflow rate is relatively low. It's certainly a lot lower than what the airflow rate would be if you're trying to also do sensible and latent cooling all on the air side. So the air movement is small. It's really not creating drafts and so forth. And I've been in buildings with these. They can be very, very comfortable. So active chilled beams, again, combine ventilation air with above dew point chilled water. There are passive chilled beams. The difference is we just don't introduce any dry ventilation air. So typically, if you're trying to add cooling capacity and you don't need additional ventilation air, you can combine some passive chilled beams with active chilled beams. Here's a photo that shows some, here's mount in I'll say in an industrial type finish where all the ceiling structure is exposed. You can see the ducting here as well as the piping that supplies these units. Or they can be suspended within a ceiling grid. And again, the upward airflow is into the center, up through the coil, and then outward on the two perimeter long sides of the chilled beam. Now, they are typically combined with what's called a DOAS, or direct outside air system. What a DOAS system does is it brings in outside air, goes through a filter, and most DOAS systems do have a some type of heat recovery system in it. And it could be a rotating desiccant wheel. And what that is doing is it is taking some of the lower temperature and lower moisture content exhaust air and using that to pre-cool, and I'll say pre-dehumidify the incoming air. So instead of just blowing air that is at a lower humidity and a lower temperature, but has to go away because it's, it's spent air from a ventilation standpoint, we're going to use some of that. We're going to recover some of that beneficial effect with this rotating enthalpy wheel and preconditioned air. It's then going to go through a fairly deep chill water coil. And when I say deep, again, multiple rows of tubing. And the idea is that we're going to bring that down to a very low dew point, lower than what a normal air handler would do. And the reason we're doing that is, again, we want that super dry air to go into the space and basically mix with the humidity in that space so that the mixed condition is at a normal interior humidity level. We're trying to maintain, for example, 75-degree dry bulb, 50% relative humidity. And we can use our psychometric charts or software, and we can figure out what are the conditions of this airstream necessary to achieve that desired air condition in the occupied space. Again, Hydronics 28 takes you through some of the calculations on doing that. Okay, so again, a combination of a direct outside air system for ventilation and for latent cooling. And of course, our coil here, remember, our coil is really going to be covered with condensation because we're pulling lots of moisture out of that incoming airstream before we send it off to that occupied space. All right. Okay. I won't spend a lot of time on this. It is out of Hydronics 28. This is fundamentally, it's a 4-pipe distribution system in a building. It has chillers, it has boilers. These are interfaced to the 4-pipe system through hydraulic separators. I'm showing a duplex pumping system here. And over on the left side, over here, I'm showing these are chilled beams. Again, we have to keep the chill water temperature to those beams above dew point. Now, the chill water main might be well below the dew point temperature. This could be 45, 46 degree Fahrenheit chill water. We want perhaps 60-degree chill water going to our chilled beams. So we need some kind of a mixing system. It could be done with a variable speed injection pump. It could be done with a 3-way motorized valve. In theory, you could do it with a 2-way injection valve. Pretty much any mixing that we would use in heating could potentially be used, probably with the exception of 4-way valves. We really don't need a 4-way mixing valve here. But a 3-way motorized valve could be substituted. And I just want to point that out. We do show it down here. I'm purposely trying to show a variety of different hardware here. You'll see the ducting that comes up from the direct outside air ventilation system. We have a cooling coil, we have a heating coil, and again, we have some variable speed circulators that are controlling the feed of chilled water or heated water to these coils. And it's controlling that flow rate based on, in cooling mode, trying to maintain a certain dry bulb, wet bulb temperature in our ventilation air. The ventilation air is being introduced to the space through dampers, motorized dampers, and directly into the active chill beams up here. And of course, there are many, many potential variations on a schematic like this. how we provide our mixing. Do we want combined heating and cooling on a radiant panel or just cooling? For example, here, this radiant panel is doing just cooling. Up here, we're connected to all 4 pipes, so we have the capability of doing heating and cooling. So again, it's a conceptual schematic, just showing you the versatility of what you can do here. Okay. The hydraulic separators that you see in here, again, they're providing the air, dirt, and magnetic particle separation, and also the hydraulic pressure dynamic separation between these different circulators. All right, we've got a few minutes left. I'll go quickly through water loop heat pump systems. Real quick summary. Small buildings like single family homes typically have what are called envelope dominated buildings or envelope dominated heating and cooling requirements. In the winter, pretty much all the spaces need heating. In the summer, all the spaces need cooling, all right? That's not necessarily the case with larger commercial buildings where we have core areas that do not have outside exposure, and yet they have lights, they have people, they have equipment, all generating heat. So we could have a situation even in the middle of the winter where we have a core area that needs cooling and we have perimeter areas that need heating. And the concept of what I call a boiler tower heat pump system or a water loop heat pump system is to move as much of that excess heat from the core area into the perimeter, as opposed to generating the heat for the perimeter separately and generating the cooling effect for the core separately. Okay, here's an example of a small horizontal water to air heat pump. There are several companies that make these. Typically in a commercial building, you'll see them suspended on tie rods from the joist, the bar joist. There's 2 pipes that supply them. Usually there's some flexible hose here just to isolate any vibration from the unit. And obviously you've got power supply to them as well. And in some cases, they are just blowing air directly into a space. In other cases, they have ducted returns and ducted supplies. So imagine a piping system like this that could have, literally, it could have 100 or more of these heat pumps connected to it. I know of a building where I used to teach at a community college that had, I believe it was 35 water source heat pumps connected into a common piping loop. So we have water circulating in this piping loop 24 hours a day, 7 days a week. It has a duplex pump system on it simply because if one pump fails, the other pump can take over. And we've got a cooling tower out here, and we have what I'm showing here is a modular boiler system or a multiple boiler system. Now, the general idea here is when we have simultaneous core cooling with perimeter heating, if we can keep the water temperature in this common piping loop, typically between 70 and 90 degrees Fahrenheit, we don't need to operate the cooling tower and we don't need to operate the boilers. In other words, we have I won't call it necessarily a perfect balance between heating and cooling, but we have enough units in cooling versus enough units in heating that the water temperature in the loop is staying within what I'll call a dead band or a neutral zone between 70 and 90. And of course, that temperature range could be varied, but that's a typical range for these heat pumps, okay? Now, if we go into a very cold day in the winter and our perimeter load becomes dominant, the loop temperature is going to go below 70. The performance of the heat pumps is going to start to drop off. And at that point, we may want to add some supplemental heat using some kind of a boiler system, okay? And the opposite of that, imagine a hot day in the summer, all the areas of the building are in cooling. We certainly don't want to add any heat. We're going to have to use the cooling tower. So we've got a diverting valve here, and we can divert some, or in the summer, probably all of that flow through the cooling tower and dump the heat outside. So again, the idea is try to stay in a neutral zone over certainly in the swing seasons. And really, it depends just as much on what the activities are in the building, what the internal heat generation rates are, and what the perimeter exposures are and so forth. If we go outside of that neutral zone, we add supplemental heat with boilers, or we do cooling with the cooling tower. I do want to point out, if you're not using ModCon boilers here that are designed to operate with sustained flue gas condensation, make sure you put a anti-condensation valve on any type of a conventional boiler. I have seen 2 of these systems where conventional boilers, in one case, cast iron boilers, in the other case, it was a copper fin tube boiler, absolutely ruined in a short amount of time because they were being forced to operate with sustained flue gas condensation. Remember, even if we get down to 70-degree water going directly into a boiler, cast iron, steel, or copper tube boiler, it's going to cause flue gas condensation. So it is important that if you're using anything but a ModCon boiler in a system like this, that you put anti-condensation protection on the boilers. Okay. Okay, now here's a variation on that. This is where we're using a geothermal earth loop in place of, or I could also say as supplementary to a boiler and a tower. Again, depending on the application, that earth loop may be sufficient to completely replace the boiler and the tower, okay? In other cases, due to space limitations or whatever, you may still need to include a cooling tower, smaller cooling tower, and perhaps a smaller boiler system. Those would go in here. I am showing a hydraulic separator between the earth loop and the building distribution loop that allows variable speed operation on the earth loop circulator. We're using variable speed circulators out here and individual zone valves on these heat pumps. Again, the hydraulic separator allows you to have different flow rates on the 2 sides of the separator. And one of the nice things about using a variable speed circulator on the earth loop is that if we only have a small portion of our heat pump system operating, perhaps it's a spring day or a fall day, we're only at 10% capacity, why run that earth loop at full flow rate? We really don't need that. We can reduce the speed through that earth loop. And I do have a slide that'll show you a potential way to control that. Before I leave this though, I really want to stress this. In a standard boiler tower system, most of that interior piping is not insulated. Remember, we're keeping that piping between 70 and 90 degrees most of the time. So we don't have a situation where we have a lot of extraneous heat loss into the space. We do have some. And we also don't have a situation where we're below dew point causing condensation. When we switch over to geothermal as our source, that changes. We can have a much wider temperature range in that loop. It could potentially go down, maybe down to even 30 degrees. And once we pull that loop temperature, that building distribution temperature below the dew point, again, we're going to have condensation unless we insulate that piping. So if you're considering using a boiler tower system, well, I should say a water loop heat pump system, and tying it to a geothermal source, make sure that your plans include insulation on that piping, and you're probably going to set up that whole system with antifreeze. I don't want to insist that has to be done, but if you're approaching a potential freezing condition on your earth loop, getting down into those low 30s, we certainly don't want to freeze up anything inside the heat pump. So that may be running with perhaps a 25% solution of propylene glycol. Next slide, and we're getting close to a wrap here. I know time-wise. It is possible to control the speed of this pump based on measuring the BTUs per hour on the earth loop side and comparing it to the BTUs per hour over on the distribution side. Actually, I should state that the other way. We could monitor what our load is to our building loop with one of the Konteka heat meters, and then we could also adjust pump speed and match that BTU per hour requirement based on pump speed over here. So I do think these concepts open up some possibilities for reducing the power input into the circulators that are used in the system. And again, the Konteka meters can tie in with a building automation system to keep track of the energy flows on both sides of that hydraulic separator. Real quick poll question. How often does your firm use water loop heat pump systems in commercial buildings? And while those answers are coming in, my computer just told me it's 2:30. Do we have an extra 5-10 minutes if we need it?
Yeah, I think so. I mean,
Okay.
people can stay on, or if they have to go somewhere, we can, we'll just kind of watch the attendees list here, but it looks like everybody's hanging in there that started out with us. So I'd say let her rip, Siggy.
All right. Okay.
All right. So 18% never, 57% seldom, 18% significantly, and 7% often. That one's a little spread.
Okay. Well, it looks like that's a little more used than the chilled beams or the radiant panel, but again,
Yep.
contemporary approaches is what we're emphasizing here. So let's wrap this up. The last one we're going to talk about is ice storage cooling systems. And to understand the rationale behind this, we look at utility electric demand curves. So imagine, a hot climate, El Paso, San Diego, and we've got a hot summer day. At night, our demand is lower. It's not zero, but it's lower. And certainly we're hitting our peaks probably 4:30, 5 o'clock in the afternoon. So we've got this large variation in electrical demand. And this has just profound implications. Peak electricity is expensive electricity. Utilities are required to have what are called spinning reserves to meet these peak demands. Bottom line is utilities don't like peaks. So what would be ideal would be to sell the same amount of electrical energy, but sell it at a steady rate. And just to kind of illustrate that, if we took the area under this red curve and just converted that area into a rectangle, it looks like roughly maybe 46% of our peak demand. If we could maintain 46% and maintain it steadily over 24 hours, that yellow shaded area would be the same as the area under that red curve. So what's the basic idea? What we're trying to do is shave off the peak demand here in red. And if you will, think about taking that area and filling in these valleys with it in these low demand areas. So we're trying to shift electrical demand from the peaks to the off-peak hours. And utilities do that primarily through rates. They're giving you off-peak or what are commonly called time of use electrical rates. And we're going to use that and we're going to combine that with a unique ability of water to absorb 144 BTUs to change from liquid at 32 degrees to ice at 32 degrees. So this graph here is really just a plot of technically the enthalpy, BTUs per pound of water, all the way from an absolute temperature of 0 up to absolute temperature Rankine of 800 degrees. And really what we're focused on is right here. When we change from liquid to ice at 32 degrees, we absorb 144 BTUs per hour. And I just want to point out an equivalent amount of heat going into liquid water where we don't change the phase of the water. You'd have to heat a pound of water 144 degrees to store the same amount of thermal energy as changing it from liquid to ice at 32 degrees. So we have a very, very good opportunity to store a lot of cooling effect at that temperature. And this is one of the commercial products that are out there. There's several companies that offer these. This is from Calmac, which is a division of Trane now. Essentially what this is an unpressurized container, and these can be very large. They can go up to 5,000 gallons. The container is filled with a long length, and these are broken up into multiple circuits, but it's small diameter polyethylene tubing. And I've been told there's several thousand feet in one of these containers, obviously the bigger containers. And the volume around this tubing is filled with water. These are unpressurized containers. And what we're going to do is circulate a 25-degree Fahrenheit mixture of antifreeze, propylene glycol, and water at night through this tubing in these containers. And what it does, you see down at the lower right, it builds what's called an annulus of ice around the tube. And the longer we maintain that circulation, the thicker this annulus becomes. And this is a much more efficient way to create ice compared to just having a much smaller amount of tubing in the container, because it maximizes the contact area between that chilled antifreeze and the water. And these can be manifolded together. You can see here's an application where they're manifolded together. And basically you build up what are called ton hours of stored cooling effect. A 10-hour would be 12,000 BTUs per hour maintained for 1 hour, or 12,000 BTUs total cooling effect. Okay. Schematically, one of the ways that you can approach this, here are the chillers. This is shown at the ice building phase. The chillers are operating. They're creating 25-degree Fahrenheit mixture of propylene glycol and water. It's being circulated through the multiple coils of tubing in the ice bank, coming back up, going through this hydraulic separator. We'll talk about that in a second. And then coming back and just simply making another circuit. So I'm showing the air handlers off at this point. That doesn't necessarily have to be the case, but in the middle of the night, the cooling load would tend to be lower. Some of the air handlers could be off, or perhaps they're all off. I do want to stress, though, it is possible to operate some of these air handlers at the same time that the ice building is taking place. All right. So we're basically building ice there. Now, the next photo is the daytime. We've shut off the chillers. These ice banks are our source of cooling. We're circulating remember, this is a mixture of antifreeze and water, so we're circulating it through. It's pretty cold when it comes out of there, 31 degrees. It's going through the hydraulic separator. And actually, let me not jump over this. We've got a temperature sensor controlling a mixing valve over here. We don't want to send 31 degree or anything close to freezing out to the coil in the air handlers. That's going to cause frosting on the coil. So we're going to mix some bypass water right here with some of the water. Actually, here's our mixing point. We're mixing some bypass water with some of our very cold brine, getting it up to 44 degrees. And now that can go off to the coils in the air handlers. Again, zone valves, variable speed pump, and we've actually got a mixing valve over here too. Now, the hydraulic separators, besides doing air and dirt separation, they are basically there to isolate the distribution circulation from this, what I'll call the main loop circulation, and from the circulators associated with the chillers when those are on, okay? And then finally, we've got a mode. If we exhaust our ice, if we melt all the ice, we can go back to 100% cooling by the chiller. The mixing valve now is in full bypass, so our 44-degree fluid straight through up to the hydraulic separator. And again, we could control the temperature here with this mixing valve if we want it to be a little warmer, and then back in through the chiller. So again, kind of a rush through that, but that's the basic idea. And I'm going to finish with our last poll question, and if we have any time, we can take some questions. Do you think radiant cooling is applicable to the commercial cooling system your firm designs? And I promise you that is our last poll question.
Hey, Siggy, while that's running, over at the IS show, I think it was 6 years ago, I was over there, and Eastman actually has a residential ice storage, and they say heat and cool your house with ice was the big banner over it, and they had this big tank you bury in your garden or your backyard, and charge it up with ice, and they promote it as the heating and cooling with ice system. And if you Google Eastman ice storage, you can see those little residential systems that they sell over there.
Sure. Yeah, interesting. They do seem to be willing to kind of push some of those concepts a little bit more over there.
Yeah.
So how's our poll looking here?
Yeah, so we got not applicable, 11%, possibly in a small number of projects, 68%, that's good. and then applicable to at least 50% of the projects at 22%.
Great. Well, again, this is going to be a market that's likely to increase as we go forward. And again, all driven, excuse me, all driven by that quest to bring that total amount of electrical energy needed for cooling down. Okay. And all right, I'm going to turn it back over, let you go through there. And
Yeah, thanks, Siggy. That was a great presentation. Quite a bit of information packed in there. But like Siggy said, it's all. And I think Mary said that the handouts you can get on the little toolbar there too for this. But this content comes mostly from the hydronics issue. But yeah,
Hey,
so
Bob.
that's.
Hey,
Yep.
before you finish up, just let the guys that are on here. We still have lots of people on. We'll take a few questions if they have time to listen in.
Yeah, I think we got a question slide coming up too, but the next one is the, so yeah, that's next month's the save the date for the coffee with Caleffi for February right there. And let's see what else. Yep, our tech support team, if you have any questions on any of our products, applications, you need support, that's our group up in Milwaukee that can certainly help. You can call them, email them. Digital version, yeah, the last two hydronics are available as digital versions on our website too. So you've got the ability to get a hard copy, we've got the PDFs on the website, and now we've got the digital version.
yeah, and I'll jump in. Guys, if you haven't looked at this, it's really nice. You can cross-reference things. It's very easy to navigate it. And I do want to mention the PDF file for Hydronics 28 is a download. You'll see it over there. You can download that PDF today if you want to get started reading through there.
Yep. Just different places that we hang out. So on social media sites that we try and participate in every day and try and keep a presence there. So if that's how you communicate, look for us there. Okay. Yeah, questions. So I know, Mark, you've been monitoring questions. So if you want to pick out a handful, we still have quite a bit of the group.
Yeah, sure. Yeah, we do. We got quite a few folks. Hey, John, chilled beam DOAS systems. Is there any other auxiliary latent cooling required for moisture removal, or does the DOAS desiccation wheel do it?
Yeah, it's all done at that air handler. You've got a deep chill water coil in there. So you're really pulling the moisture out at the coil in the DOAS unit. To my knowledge, there's no other coil system used for dehumidification. So okay. I kind of simplify it. You're sending super dry air into the space. And again, think of it as a dry sponge. It's going to mix with the air that's in there and the moisture content of the air so that the mix of those two is establishing and maintaining a normal 75 dry bulb and 50% relative humidity.
Okay, so with the fan inside of the DOAS, would there be much difference in, I assume he meant efficiency, comparing a chilled beam system to a fan coil system?
Yeah, because what you're doing too is you're bringing down the volume of air that you're distributing. You can bring it down closer to what the ventilation requirements are, because a high percentage of your cooling is sensible cooling. So yeah, there's a savings from the standpoint of distribution energy use. Again, leveraging that hydronic side for the majority of the sensible cooling. You're always going to get some sensible cooling at the coil in the DOAS unit, but the overall savings is in terms of electrical energy use is definitely lower with the combination of the DOAS unit with either radiant panels or with the chilled beams doing the majority of the sensible load.
Okay. Speaking of latent and sensible, how do you control the cooling loop? I think you had a slide in there about controlling the cooling loop temperature to be 3 degrees above dew point. What type of hardware is used in doing that?
Yeah, I've seen a variety of it. Ideally, what you should do is have a system that is looking at both dry bulb temperature and relative humidity in the space and calculating a dew point temperature and then controlling some kind of a mixing device. Now, it could be a three-way motorized mixing valve, or it could be a variable speed circulator, but you're essentially calculating what the current dew point temperature is in the space, and then you're steering your chilled water temperature that you're supplying to either the radiant panels or the chill beams, maintaining about a 3-degree margin, 3-degree Fahrenheit margin above what that dew point is. So it's basically monitor it, calculate what the dew point is, and maintain that 3-degree margin above the dew point. That's the ideal way to do it. I have seen some systems where they simply set a set point temperature that is typically in the mid 60s, and they just go with a set point temperature. In most cases, that's probably okay. I always get concerned though. One of the things, if you're going to be doing this, you want to think about different zones in a building and how the dew point in those different zones can change. For example, if you have an entry foyer in a building and there's a lot of traffic at certain times of the day through that entry foyer, that's going to introduce a lot more outside air, and potentially you're going to have a higher dew point temperature there than you might have in a core space. So you really have to think through, from a zoning standpoint, is it adequate to have a single dew point measurement in a building? And it might be, depending on probably the compartmentalization and where potential moisture generation is occurring. Or do you want to go into a zoned type system and have multiple mixing devices that can independently respond to different dew points? Certainly in large buildings where you've got maybe a lot of moisture being generated in cooking, or a gymnasium, a pool, something like that, obviously I would zone that separately as far as controlling the dew point.
Okay, a little bit different, changing gears on questions here. Real simply, you talked about water to water heat pumps. Are there any manufacturers of 1-ton water to water heat pumps that you know of?
Boy, 1 ton, that's pretty small. I honestly don't know of any off the top of my head. Probably 2 ton, maybe 2.5 ton are available. I don't know of anybody that's building a water to water heat pump that's only a 1 ton. It'd have a very limited application.
Okay, and speaking of that, there's another question here that says, is there a minimum square foot footage to be effective for cooling a structure? Is there like a smallest size you don't even want to bother?
I honestly, I wouldn't know what that would be. It's really going to be a matter of, what kind of interior conditions do you want to maintain, and also what are the moisture sources and the heat sources in those space. I mean, you could think of a small commercial restaurant, for example. You got the pizza ovens going, you got 30 people. It could be 1,000 square feet of space, so it's pretty small, but it's got a lot of heat gain. So no, I can't think of a minimum square footage where cooling just wouldn't apply.
Okay, we just got an answer to a prior question. Well, Carrier offers water to water heat pumps starting at 2 tons. This listener says. Question: speaking of hydronic cooling with in-floor slab, can you use wood flooring? Is that recommended? Is that possible?
That's a good question. I honestly don't know. I would, in thinking about it, one of the things that would immediately be a concern, I should say a consideration, that would be, what's the R value of that flooring? Radiant cooling, you really don't want to have significant temperature differentials involved. That's why they go to that closer tube spacing. The charts that I've seen only go up to about an R1, and that would be pretty thin flooring. I would think you would be okay based on you're not going to create moisture if you're controlling the slab properly, And bringing that slab down into the 60-degree range, I don't see where that would cause any undue stresses on the wood floor. I think the bottom line on that would be to talk to the wood floor supplier and make sure that it would not be a violation of some warranty clause. I do know some of the wood floor suppliers, they put what I consider kind of an arbitrary temperature limit of 85 degrees on their products. And there are going to be many applications in heating where those floors are going to go over 85, and that could potentially violate that warranty. But there's also going to be many situations where the floor is going to go over 85 without any floor heating. Just think of a wooden floor in a southern location. So to answer the question, to summarize, I don't think it'd be a problem provided you can keep the R value as low as possible and make sure that the product remains under warranty in that application.
Okay, we got a comment now. Wood would be bad. Need bare concrete for heat transfer. Perhaps someone that has experience.
Absolutely correct. The best R value is no R value, so I would agree with that.
So there's a company over, a British company that makes a heat pump called the Shoebox heat pump. And they claim to be the world's smallest ground source heat pump. I think 3 kW is their smallest one. So if you Google Shoebox heat pump, you'll find a tiny little heat pump if you have a need for that or you want to read about that.
3 kW, yeah, that'd be right around, it'd be a little under a ton, wouldn't it? That's for a tiny house, huh, Rod?
There you go, yeah.
Geothermal tiny house.
John, do you know much about borehole heat exchangers?
I don't know a lot about them. They are, they're commonly used with commercial and some residential geothermal. Basically, the idea is you bore a hole in the ground, you put tubing down there that has a tight fusion bend at the bottom, pressure test it, you grout it, and that becomes your probe or your heat exchanger for the geothermal heat pump. Now, there are design manuals that can quantify, based on what kind of soil conditions, how deep the borehole is, the diameter, and so forth. If you're looking to design a system like that, I know the ICSPA group there at International Ground Source Heat Pump Association, they have a design manual that covers that. And there's also several companies that have software that can evaluate the thermal performance of boreholes. The math is pretty complicated. It's typically going to be something you want to simulate with software.
Here's a question I think a lot of people will find interesting. This is in regards to a specific region. Overall, can a radiant cooling system installed in Southern Ontario maintain internal comfort when only paired with a dehumidification system? The building envelope is very tight and highly insulated.
I think it probably could. Is two things: to make sure that you don't get down to the dew point with the floor, and that the dehumidification system that's being used is maintaining a reasonable comfort level of humidity in the building. I don't see why that would be a problem. It's really not a lot different from the DOAS approach, other than they're using a separate, probably refrigeration-based system to do the dehumidification. So yeah, I think it could work. But again, I go back, what kind of interior conditions are you trying to maintain, and making sure that any of the radiant panels or chill beams, for that matter, would not operate with sub-dew point conditions.
Okay. There's some questions concerning dew point control and controls. Here's one. What type of controller choice is recommended to keep the radiant cooling ceiling panel below the dew point room ceiling temperature? And there's a couple other related questions as relates to the types, probably brands of controls that are out there.
I'll tell you what I know. I have not done a lot of recent research on that, but I believe both Tecmar and HBX have standalone controls that I've been told can do that with humidity sensors and temperature sensors, and then some type of an output to a mixing device. I believe Honeywell does have a standalone controller that can do dew point as well.
Okay.
I think in the majority of these systems, most of this is going to be done with code in a building automation system, where sensors are going to provide relative humidity input and dry bulb temperature input. And then the graphs that I showed, those can be easily transferred over to equations. So if you know dry bulb temperature and you know relative humidity, you can immediately calculate what the dew point is. So at that point, you have in a sense, you have a target value. So take that value, add 3 degrees Fahrenheit to it, and that's what you're trying to maintain on the outlet of your mixing device. And you simply use a PID control loop to modulate the mixing so that you're maintaining that supply water temperature 3 degrees above what that dew point is. So I think, again, commercial buildings, most of that is going to be done with building automation system code. But if you're looking for a standalone device, Tecmar HBX controls, and I forgot the series number with Honeywell, but I believe they have a series of standalone controls, one of which is set up for dew point.
Okay, a couple comments on some of the questions we just asked. Jim says Tecmar controls will work. We have used them in a radiantly heated and cooled home using temperature and humidity at each of the home zones. So thank you for that, Jim. Another one here is a person that's doing a lot of, this is Jeff. I do radiant cooling in New England a lot. And this is related to, I think, humidity. Where am I at? Key is good DOAS and the in-floor tubing material with low R value. That's key for him up in New England.
Okay. Yep. Yeah.
Let's see here. We got maybe just a couple more minutes, maybe 3 more minutes here, John.
Sure.
Did we miss any of the pre-submitted questions that came in? Probably a couple. Let's see if I can jump to some of those here. We talked about separation of air in chilled water systems. Is there a temperature at which they become ineffective that you know of?
Separation of air. I'm not sure I'm following that, but
I think it's just the idea of using air separators in a chilled water system in terms of the.
Okay. Yeah. Separating air from the water.
Yeah, air separator.
Well, I don't know if there's, I wouldn't really say there's a temperature at which it doesn't work, but the efficacy is definitely a function of temperature and pressure. And the lower the pressure and the higher the temperature, the lower the solubility. So in a chilled water system, even though the return water might be 60, 65 degrees, that's still going to have a lower solubility for air than chilled water at 45 degrees. So air separation in a chilled water system would be on the return side.
Yep, and as we know, every hydronic system in time will receive some type of intake of, at a minimum, oxygen if it's completely tight through, but also through the seals and what have you. So that's a good question. Maybe a couple more here, John. Is there a rule of thumb for BTU per square feet of cooling? Is there just rough rule of thumb?
No. When I hear rule of thumb, I usually say, rules of thumb are for designing thumbs. But the thing is, you really, cooling loads are more complex than heating loads. So with a heating load, it's essentially looking at the R value of the building surfaces. You're looking at the inside-outside air temperature difference, and it's a pretty simple, straightforward calculation. With cooling loads, even residential cooling loads, you have that sensible conduction, through the building envelope. So you have a inside-outside temperature differential. You have an R value of the different surfaces. But on top of that, you have solar gain, and that's going to be a function of the building's orientation, as well as the windows, the shading of the windows, the type of glass, that's used in the windows. So that's an additional factor. And on top of that, you have moisture. Basically moisture that infiltrates through the building envelope just by diffusion. You have moisture being generated, cooking, showers, people. So a cooling load calculation is really where you need to go to establish that. I would not go out and say, you know, I actually heard somebody the other day say 40 BTUs per hour per square foot for heating, 20 BTUs per hour per square foot for cooling. That is a, you know, that's a shot in the dark. I would not design a system, especially a commercial system, around anything like that. I would start with load calculation software is really the practical way to do it. Most programs today, if you're dealing with any type of incentive program through a state agency, most of those will require ACCA manual J calculations on cooling load or heating load. They seem to recognize manual J as the standard. And there are several softwares on the market right now that are approved to follow manual J. That, you know, that's an approach that I would use for a residential cooling calculation. In commercial, it becomes even more complicated because you have time variations between when energy gains occur and how that affects the interior air temperature. In Hydronics 28, we talk about a couple different softwares that are available, commercial softwares that are available. I do know that Carrier has got a commercial cooling software available. I believe Elite Software in Texas has another one, and I'm sure there are others. I'm sure Train has some as well. But you don't want to do the rule of thumb thing with either a heating load or cooling load, but especially a cooling load, because you know, again, solar gains, moisture gains can make a huge difference in what that load is.
Good points. Well, it's top of the hour, or a little bit after. There's a number of questions that have come in again, and we have a few that we didn't get as far as pre-submitted questions, John. So I think, in the interest, I guess, time and finally calling it a day. It went 2 hours, and we just dipped down below a couple hundred folks. So I'll turn it back over to you, Bob and John, to wrap things up.
Well, thanks, Mark.
Yeah, thanks, E. That was a great presentation. A lot of good information, timely information, of course, because the electrification is becoming a big hot topic in our industry, and we want to certainly be at that table. So this is some good ideas on how we can stay in the game with hydronics as we go to more electric-only options. So.
Yep, and just a reminder again, the PDF of the slides, as well as the PDF for the Hydronics 28 that we talked about. Those are both up there for download.
Yep. All right.
Okay.
Well, I think we'll call this a wrap, and thanks everybody for joining us today. And we'll see you maybe next Monday on our shop talk, and then we'll see you in February for the next Coffee with Caleffi. Thanks everybody. Have a good day.
Thank you. Take care.
Bye-bye.